Hello
Good
guys,
afternoon.
see you.
Good afternoon. How are you?
Good afternoon.
Okay, thank you. How are you guys?
Normal.
Good afternoon.
Good afternoon. So, last time we made an introduction of magnetic field. Have shown and quantified magnetic force, which is acting on a moving charge for magnetic field. And today we continue studying like interaction via magnetic field. However, today we will deal with a continuum of charges which travel inside a conductor, and we will quantify magnetic force which acts on a conductor with electric current. So obviously, if we have electric current in a conductor, we have moving charges. If electric charges are moving, they will experience certain magnetic force exerted on them. So if we have a conductor in external magnetic field, then there will be per unit length of this conductor, there will be some magnetic force, which our job for today will be to calculate. And also we will focus on calculating torque of a current loop. So we will show that if we have some current loop, we can calculate, like create some torque, which means force multiply shoulder. And that feature could be used to develop some electrical actuators like motors, or some measuring systems like amperemeters. So all this we will discuss during today's lecture. Let me switch to the slides. So magnetic force acting on a current carrying conductor. So we know that the magnetic force, which is exerted on a charge moving with some drift velocity vector, is quantified according to this formula. So we have magnetic force vector equal to electric charge of this particle, like electric moving charge. Then we have vector product of drift velocity vector and magnetic field vector. So in order to calculate the total force acting on the segment, like some unit length of a conductor with some electric current flowing through it, we need obviously to multiply this magnetic force exerted on a single electric charge by number of electric charges in this segment of the conductor where we want to calculate, for which we want to calculate the exerted magnetic force. So in this case, we will have the following. Magnetic force will be equal, so we can put in parentheses magnetic force exerted on a single electric charge, Q times VD vector cross product with B vector, and total number of charges in the segment of conductor. So we use N, which is concentration of charge carriers per unit volume. And then we need to multiply some volume, which is cross section of the conductor times length of the conductor of the segment which we analyzed. So from previous discussions, we also know that electric current can be given as electric charge times concentration times VD times A. So means product of electric charge, concentration of charge carriers, their drift velocity, and cross section of the conductor. So taking this into account, we can rewrite this equation in a bit different way. Will be magnetic force vector exerted on a segment of conductor with electric current will be equal to electric current, magnitude, times L vector cross product with B vector. So what does it mean? That magnetic force exerted on the segment of a conductor will be defined by magnitude of electric current and cross product of two vectors. Magnetic field vector, it's clear what it is. This L, capital L vector, is the vector which points into the direction of electric current and has magnitude equal to the length of the segment of this conductor. So now we need to make one more step and consider some general equation, because conductors may be not straight and they can bend in different shapes. So we want to consider like very small segment of a conductor. Let's say this is our conductor, which is not straight. Then we have some magnetic field vector. And we consider some small segment of this conductor. Let's denote it as ds vector. So there is some current flowing in this conductor I. So this ds vector orientation coincides with the direction of electric current flow in this area of the segment. And the magnitude just defines the length of this segment. So some small magnetic force which is exerted on this small element of the conductor can be described as dF magnetic is equal to I times ds vector times cross product with B vector. So can someone tell me, please, why do we put here I as a just coefficient? So why we don't consider electric current for each segment individually? Any ideas? So it's actually, it doesn't matter which segment on this conductor we will consider. the magnitude of electric current will be the same. So that's why we can use it as just coefficient in front of this cross product of two vectors. And that will be correct. So it could be that if, for instance, we have different cross section, we will have different current density, which we discussed previously. However, the total current will be the same at any cross section of the conductor. So what is important to highlight from this equation, that this magnetic force acting on some segment of a conductor will be always perpendicular to the plane defined by vectors bs and b. That comes from the properties of the cross product of two vectors. So now, if we want to calculate total force which acts on the conductor from point A to point B, we need obviously to integrate this cross product. So total magnetic force exerted on the conductor between points A and B is given as I, so we can take it out from the integral since it's a constant, from point A to point B, ds vector cross product B vector. So that is the general equation, which in all cases will show, will give us a possibility to calculate total magnetic force exerted on conductor with current, regardless of its shape or length. So now let us consider some example how we can run these calculations. So our model will be the following. So let's see, let's have some system of coordinates. Will be coordinate x, coordinate y. Let's say we have here coordinate z. And we have some like two conductors connected with each other. So that will be one conductor in a shape of semicircle and another conductor, maybe let me make it colorful, will be a straight line. Okay, so we extend here axis x. The radius of this semicircle will be some capital R. So here will be coordinate minus R. Here will be coordinate R. So let us consider that there is some electric current flowing through this loop, because these conductors are connected, so they form some loop. And here we have current in this direction, and obviously it flows further in this direction. So now let us consider that we place this system in some external magnetic field, which is oriented along axis y. So let's see. If we apply this left-hand rule for determining the direction of magnetic force, means if we align our like fingers of our left hand along electric current. So now I'm talking about conductor number 1. Let's say this is conductor 1, this is conductor 2. But actually this rule is applied to any cases. So if we place our 4 fingers in the direction of electric current, in that way that magnetic field vector penetrates, like goes into our palm, then the thumb at right angle shows us the direction of this magnetic force. And in this case, we see that the force which is exerted on segment 1 of the loop, like first conductor, will coincide with the direction of axis z. So this will be F1. If we repeat the same procedure for this loop, part of the loop, conductor number 2, then we will see that the orientation for force F2, which is exerted on segment 2, will be in opposite direction. So that will be F2 vector. And let us now try to determine the magnitude of these forces. So F1 vector, according to the equation which we derived on the previous slide, should be given by the product of electric current to integral from one end to another. So we do this for the first conductor. So we should integrate from minus r to r. Minus r, r. R is the radius of the semicircle. Then we have here ds vector cross product b vector. So what is important to highlight here, that direction of current and means direction of this ds vector always will be in parallel to axis x, and that means it will be perpendicular to magnetic field vector b, because magnetic field vector is aligned along axis y. Taking this into account, we can substitute this cross product with just the following. So we have I integral from minus r to r. Here will be just magnitude of magnetic field and times dx. So we can substitute ds with dx. Since they are perpendicular, sinus 90 degrees will be unity. So we just operate only with absolute values, like magnitudes of these vectors. And all this we can also multiply by k unit vector, which shows that this F1 vector will be aligned along axis Z that we determined previously with the help of left-hand rule. So now we need to integrate this, and we will get the following. So this will be, actually we can take out the like b from the integral because it's a constant. So we have I times b integral minus r to r dx, and here we can add also vector k, unit vector k. That will be equal to I times b unit vector k, and will be r minus r. So actually we will get 2 times I b times r times k unit vector. So that is the expression for F1 vector, means of the force, magnetic force exerted on first segment of this loop. So now we need to proceed further and calculate the F2 vector, force with magnetic force exerted on segment 2. So now let me probably delete this part here, because we will need some space inside this plot. So is some small force F2 exerted on a segment of conductor number 2 can be given as I times ds vector cross product b vector. So now it is necessary to define this ds vector, because we don't have any straight line here, so we need to think how we can deal with this. So we consider some radius r of this semicircle. Then here we will have some ds vector, which will be defined by some angle. Let's call it d theta. So ds, like magnitude, will be given by r, radius, times this angle d theta, if we consider angle in radians. So taking this into account and assuming this configuration when we have now different orientation between ds vector and magnetic field vector. So if we now consider this ds vector here next to magnetic field vector, this will be some angle between them, and it will change if we go from one side of the semicircle to another side of semicircle. This angle will change, so that should be taken into account. That's why we can just continue here. So it will be electric current times magnitude of magnetic field times magnitude of ds vector times sinus theta, angle between two vectors. Here we also need to add minus k unit vector, because we have already shown previously that F2 vector will be exerted on the second segment of this loop and will be aligned in opposite direction to the direction of axis z. So that's why we put minus in front of k unit vector. So with this, we can go further, and instead of ds, substitute this expression, which gives us relationship between ds and small change of angle theta. So in this case, we have I, we can put minus probably here, I times b times r times sinus theta, and here is k unit vector. Oh, sorry, I forgot about d theta. So sinus theta times d theta times k unit vector. So now we have expression for this force exerted on a small segment, ds, and in order to calculate the total force exerted on segment 2, we need to integrate this expression from one edge of conductor to another. So how it will, we will define this ranges of integration. We go from 0 theta to pi, which will be 180, means we have semicircle. So let us write on the next slide this integral, which we need to integrate. So that will be F2 vector will be equal. So we have this minus in front, we keep it in mind, from 0 to pi.
I'm sorry, shouldn't it be minus from minus pi over 2 to pi over 2? Since it's angle between b vector and f vector.
Yeah, you can also do that too, but it's just matter of our choice, from where we start to count. The most important that should be pi as a difference between initial and final point. So here we can go from as a minus, but it just makes it easier to go from 0 to pi. So we start from this the part that will be our 0, and then we go to this part where this angle will be just pi. So between this radius vector, which we use, and axis x. So that what kind of makes sense here. So we don't have plus minus in the range, we go from 0 to pi. So let me write it down here. That will be, oh, I forgot to look here. So IBR sinus theta dt. Okay. IR sinus theta d theta. And we can, here we have k unit vector. So let us take out all constants from this integral. Minus I times b r k unit vector integral from 0 to pi sinus theta d theta. So when we integrate I b r k unit vector, here integral will give us minus cosinus theta, and that will be from 0 to pi. So this will be I b r, minus and minus we cancel, cosinus pi minus cosinus 0, and here k unit vector. So these guys will be minus unity and unity. So we eventually will get 1 minus 1 minus 1 minus 1, so it will be minus 2 times I r b and k unit vector. So as you see, the magnitude, so direction is different because we had plus previously for f1. Now we have minus k unit vector. However, if we check for magnitude, we have 2 times I br, and the same is here, 2 times I rb, doesn't matter. So what is important to highlight from this example, that the force acting on the current conductor is equal to the force acting on the straight conductor between the same two points. And if we add these two vectors, f1 plus f2, that will be equal to 0. So this is a general rule that the net magnitude force acting on any closed current loop in uniform magnetic field is equal to 0. So some net force is equal to 0, however, not torque equal to 0. So let us now try to calculate torque, which is exerted on a current loop. So let us consider some rectangular current loop. So we have some, like, we can name this conductors like segments 1, 2, 3, and 4, and have some current I which flows through this loop. Also, we have some uniform magnetic force, magnetic field. And now let us check what will be the forces exerted on each of these segments. So we can eliminate segments 1 and 3, since they are like electric current in these segments is parallel to magnetic field. So there will be no force exerted on segments 1 and 3. There will be some force exerted on segments, sorry, on segments 2 and 4, because they are like electric current in these segments oriented perpendicular to the magnetic field vector. So we can write that in absolute magnitude. So let's this is length A and this is length B. So in absolute magnitude, this force is F2 is equal to F4, and that is equal to electric current I times A, which is the length of segments 2 and 4, times B, magnetic field strength. So now, if we take a look on this from the bottom, so that will be kind of look from the bottom. So this is conductor 3. And consider that it's fixed at some point O in the middle, so it can rotate about axis which goes through this point O. So here, electric current will kind of go out from the plane of the image, and here electric current will go into the plane of the image. So if we consider the orientation of our magnetic field, this current direction, and determine the rule of left hand, we will see that the magnetic field F2 on segment 2 will be pointed here. This is F2 vector, and there will be another force acting on section 4 will be down here. So it will be F4. So now we have two forces which are equal in magnitude but opposite in the direction. And with respect to this point O, these forces will create some torque. So magnitude of this torque will be F2 times half of the width of this segment 3 and 1. It will be B divided by 2 plus F4 times B divided by 2. Assuming that magnitudes of these F2 and F4 we know, that will be I times A times B. Here will be B over 2 plus B over 2. And eventually we get I times A times B times capital B, which stands for magnetic field. And this is nothing else as the area of this loop. So that's why we can write that we have I times A area of the current loop times B magnetic field. So that is the expression for torque, and that will be the maximum value for torque. We can write here T like tau maximum. In order to calculate other possible values, we need to assume that this current loop starts to rotate about axis, which goes through point O. So let me clean some space here. So we can maybe delete this part. How it will look. So we have already tilted. It's also look from the bottom of the current loop. So this is our point O about which this current loop is rotating. So here we will have current coming out and here going in. And there, so also we have some angle between normal to this current loop theta. This is force F1. This is force, sorry, not F1, F2. This is force F4. So now the shoulder for this force F2 and the same for F4 will be, here is angle theta also, and the shoulder will be smaller because we have B over 2 times sinus theta. So now the shoulder reduced, and that's why we will end up with smaller value of the torque. So we can write for torque now that will be equal to I times A times B, like magnitudes of F2 and F4, times B over 2 times sinus theta plus B over 2 times sinus theta. So that assumes already this option for changing the orientation of the current loop. And that obviously will change the shoulder of these forces. So eventually we get I times A B times magnetic field magnitude times sinus theta. And also this is area of the current loop will be I times A times B times sinus theta. So in general, if we want to get torque vector based on these findings, we can write that torque vector is actually equal to electric current magnitude times vector product of A and magnetic field vector B. So this equation gives us torque in vector form, and this vector A is actually always perpendicular to the plane of the current loop, and its magnitude is equal to the area of the current loop. So the way how we determine the orientation of this vector A, we can see in this figure. Now I will share with you my screen. So if, for example, we have any current loop, so when we curl like fingers in the direction of the current around the loop, then of the right hand, then the sum at right angle shows us the direction of this vector A, which is applicable in the scope of the previously calculated, previously derived equation. In order to determine the torque vector of a current loop, so that is applicable for any shape current loop. So here is showing some circle, but it can be also rectangular or any other shape current loop. So with this, I would like to summarize. So we discussed the magnetic force exerted on segments of conductor with electric current, have shown that it will be equal to the product of I times electric current times integral from point A to point B of vector product ds, like small segment vector, and vector B of magnetic field vector. ds vector has direction of electric current direction in this given segment of the conductor, and its magnitude is equal to the length of the segment. So when you integrate, you can actually calculate total magnetic force exerted on any shape conductor with electric current placed in external magnetic field. So also we calculated the torque, which is created, exerted on a current loop placed in a uniform magnetic field when we have some current flowing through the current loop. So in general form, in vector form, torque can be represented as a product of electric current with a vector product of magnetic field vector and vector A, which is has magnitude of the area of the current loop, and its orientation is defined by this right-hand rule, which was shown on the image at the slide. So this is the short summary, and further we will proceed with the calculation of magnetic moment of the current loop, but that will be already our next discussion. So if you have questions, you are welcome. Yeah, we will continue discussing these magnetic properties also next time. So that will be on Wednesday. And thank you for your attention.
Thank you.
And have
Have a nice day.
You too. Bye-bye.
Thank you. Bye-bye.
See you later. Goodbye.
Goodbye.
Bye. Take care.